taking the limit of the difference quotient, you started to see that most of the functions that we use were fairly easy functions. Linear function, sometimes we may have gotten crazy and done a cubic or a quadratic. But you can imagine that if you had to do that for a big scary function. What if my function, for instance, was like 2x to the 2/3 minus 7x to the -4. Okay, that difference quotient could get pretty ugly. So of course, to make our lives easier, we come up with a bunch of shortcuts. And that's what we're going to talk about today. So today we're doing basic differentiation rules and rates of change. I think you'll like this because it will make your life a lot easier. Whole bunch of stuff to get done today. So we're going to do the constant rule, cakewalk. We're going to talk about the power rule, probably the single most important theorem that you will use in first semester. Constant multiplication rule, silly, easy. Sum and difference rules, that's easy too because it's the same thing we've done 35 times already. Okay. The derivative of a sum is the sum of the derivatives. Yeah, we got to do some trading. Sine and cosine. What was that?
It's a rock. It's literally a rock.
Why do you have a rock?
I just hold it sometimes.
It's like a stress stone?
Yeah.
Nice. And you're so stressed you threw your rock on the floor?
Yeah.
That's bad.
Yeah. He's getting your rock.
Good guy. We'll do some, once we get all this other stuff done, then we'll come and talk about rates of change and how derivatives relate to rates of change. And then we'll talk about some physics, sorry. Or yay, depending on how you feel about physics. All right, constant rule. So before I click, let's talk about taking the derivative of a constant. So let's take the function y equals 7. That's a constant function. What's the derivative? So hopefully you're not in your head plugging it into the difference quotient and then taking the limit of all that junk. That's the function, yeah. Just a constant. Any number you'd like. Why? Good. Did everybody hear that?
No.
No, say it louder.
It's 0 because it's a horizontal line.
Any constant is going to graph a horizontal line, and the slope of the tangent of any horizontal line is going to be 0. Now that seems kind of silly to even talk about this, but we need to use it later on. Okay, so horizontal line, 0. So here's one notation. The derivative of the constant with respect to x will be equal to 0. Take the derivative of any number, you're going to get 0. It doesn't matter what the number is. Okay. Y equals 7. Derivative is 0. F of x equals 0. The derivative of a constant, 0 is a constant, is 0. So notice I changed the notation here. Stayed with y, got dy dx. That's Leibniz, by the way. Then did f of x, got f prime of x, Newton. I actually learned from Mr. Grass the other day that Newton didn't use an apostrophe. He put a dot above the f, and then 2 dots and 3 dots and 4 dots, and just kept putting dots up there. If we have s of t, so just change the name of the function, and actually this will come in when we're talking about our physics stuff here. I've got a function s that relates to time. Actually, our position function is -3, then the derivative is 0. Okay, and I'm kind of beating a dead horse here, but I want to make sure you understand. What's a derivative of pi squared? 0. Why? This gets people every time. Jimmy?
Because pi is just a number. And so
Pi is just a number.
Yeah.
Good. As is e. Okay, those pop up every once in a while. People want to start using all these fancy derivative things to take the derivative of pi squared, but it's just 0. It's constant. Okay, any problems there? Okay. Again, I know I beat a dead horse with it, but it's kind of important before we move on to this bad boy. This is life altering. You'll love this. And it's really easy. There's the calculus. I'll do it in English in a second. Actually, let's see if you can do it in English. So there's the calculus. N is a rational number, and we have a function x to the nth power, and it's differentiable. How do you know it's differentiable? Because it tells you it's differentiable in the first line. It says that the derivative of x to the n is nx to the n minus 1. What does that mean in English? How do I take the derivative?
If it was like x to the fourth, the derivative would be 4x to the third.
Beautiful. Bring the exponent down, reduce it by 1. You want that again? Bring the exponent down, reduce it by 1. Okay, so here it is in the calculus speak. Bring that n down in front, reduce that by 1. Now what we get to do is a bunch of derivatives using the power rule. Oh, see how important that is? Because it flashed, so it's got to be important. Okay, what's the derivative of x cubed? Nope. 3x squared, correct. Okay, now compare that to the homework problem you had where you had to plug in x plus delta x, cube it, subtract x cubed from it, all over delta x, cancel things, factor out a delta x, cancel the delta x, take the limit as delta x approaches 0, and you do all that and it spits out not the answer. Apparently I don't have the answer there, but I do have a pen in my hand that we can write it down. F prime of x is equal to 3x squared. Okay, good. Click on that. Get that away. Come over here. All right, how about that guy? G of x is the cubic root of x. What will I do? What will I do?
Isn't a cube root just x to the 1/3 powers?
Excellent. Keep going.
So you can do 1/3 x to the negative 2/3 power.
Threw an extra step in there. Rewrote the function as x to the 1/3 because they're the same thing. And you said the derivative was what, Maggie?
1/3 x to the negative 2/3 power.
Well done. Yeah. One, as my grandfather would say, 1/3 minus 1. It's negative 2 thirds. One thing we'll learn later on, I'm not going to hype on it right now, but eventually this won't be an acceptable answer because we don't want negative exponents. But for now, we're gonna crawl before we run here. Okay, good. And how about that guy? Did I just get whoop out of somebody?
I was yawning at some time.
Oh, I thought it was like you were scared of 1 over x squared.
Sort of.
You are, but it doesn't warrant a whoop.
No.
Okay, good. What do I do now? Greg?
Would it just be negative 2x to the first, negative first? 1 less 2.
I don't know, you're driving the bus.
Negative 2x to the negative third.
Can I give you a helpful piece of advice?
Probably.
Okay, well, let me know. How about we rewrite the function first? Okay? What would that be, Greg?
X to the negative second.
Okay? So therefore, h prime of x would be what?
Negative 2x to the negative third.
Okay. Because negative 2 minus 1 is negative 3, not negative 1. Easy, yes? Good. This is probably the only thing that people are going to screw up on here is I'll always get a negative 1 there because people can't subtract.
Yeah.
You can do calculus, you just can't subtract. Whatever. Pregunta, senor.
What happens if your function is just like 2x?
That's such a good question, I'm going to change colors.
You made it
Okay? So what? Oh, yeah. That's x to the what? Good. So what's y prime?
Is it just 2?
Y?
Because x to the 0 is just 1.
Now that's applying the rule. Let's think about it graphically. What is this? It's a line, right?
Yeah.
Okay, what's the slope of that line? 2. And therefore the slope of the tangent line to that line would be its own slope for that line being its own tangent line, so therefore you would get 2. But according to the power rule that we just used, you would get, bring the 1 down, multiply it by the 2, 1 times 2 is 2, reduce the power by 1, x is 0, 1, x goes away, 2. Good question.
Just love it.
Okay, consummate, actually this was a beautiful segue. Thank you for the help, Michael. Almost like you planned that. What happens if there's a constant in front of the function? Okay. There's the fancy schmancy calculus. If you've got a constant times a function, just take the derivative of the function and multiply your answer by the constant. Okay, so in essence what he asked me is, what's a derivative of x times 2? Well, the derivative of x times 2 would be the derivative of x times 2. Okay, so multiply your answer by 2. So the constants in front don't matter. They don't affect anything. Does that make sense? Yeah? No? Let's suppose I want to take the derivative of 3x squared. Don't let that little bugger bother you. Just do the derivative of x squared and multiply by 3. What's the derivative of x squared? No.
Oh,
2x. And then multiply that bad boy by 3 and you get 6x. That's it. Yeah, just multiply. Okay, we good there? Too fast? All right, I'll go slower. There's a whole bunch of fun.
Wait, can you go back for a second? I didn't finish writing. On the slideshow.
Are you gonna do the splits?
Unless you're ready to call 911.
So which answer that for?
Can't call 911, so you just let me lay there and scream. Oh, sorry, I skipped all that. Do I know that girl? I have no idea who that girl is.
Go yell at her, she takes the phone.
I don't know who she is. How am I gonna find her?
You're not doing anything, I look forward to the splits.
Yeah, that's true. Okay, here we go. Y equals 2 to the x minus 1. Right? Sometimes it will be helpful to rewrite the function before you take the derivative. So therefore, a little bit of practice. What's y prime? And if you're feeling saucy, you could write it that way. But we don't care about that right now. We'll get to that stuff later when we start cleaning things up. Part B. F of t is equal to, I'm going to rewrite it as 4/5 times t squared. Therefore, whoops, that's supposed to be a t. Bushly. Mary, what's f prime of t then?
It would be t or 2t times 4/5. So 8/5 t.
Wunderbar. How do I rewrite y? I'm sorry, yeah, y. How do I rewrite that function in part C? Jimmy?
Equals 2x to the 1/2.
Sorry. Y equals 2x to the 1/2. And what's y prime, Jimmy?
Y equals x to the negative 1/2.
Which if you're feeling saucy, it would be 1 over the square root of x. But again, Mark, question? Say it again, I'm sorry.
Why did it equal to the -2?
Because -1 minus 1 is -2. Okay. I don't know if you can see the green, but we'll try it. For D, you see that? No?
Not really.
Yeah, that worked really well.
You click OK.
I didn't click. Is that what happened? All right. Blue. There we go. Okay, how do I rewrite D? Amanda?
2x to the negative 2/3.
I'm sorry, that is incorrect. Close though.
Is it 1/2 x?
There you go. 1/2 x to the, what'd you say?
Negative 2/3.
-2/3. Okay, Amanda, so what's y prime?
Negative 2, 6 x to the negative 5.
What's 2, 6?
Oh,
1/3. Yep. Well done. Michael, back to you. What's the derivative of -3/2 x?
It's just the derivative of -3/2 times x, which is just -3/2.
I lose anybody on any of those? Or any of those you need to review? Okay. D? Let's go back to Amanda. Amanda, what do you got for us? Let's start with the 1/2. Are we okay on the 1/2, Greg?
Yeah.
All right. So you're wondering where she got x to the negative 2/3?
Yeah.
Go, Amanda.
If you look at the other one, the one right before it, that's x to the 1/2, so it's really the square root of x to the first. So it's the same as x to the 2, 3. Because the 2, when you see something like that, the 2 is the numerator, and then the square root power is the denominator.
Get that?
Sorry, I didn't explain them all.
Oh, and since it's next to the first time, we have to decide this one.
Throw a square in there.
Yeah.
2 fifths. Okay. Raising it to a power is the numerator. Roots are denominators.
How did it become negative though? Is that because it's
You got it, because it's in the denominator. It's fun, right?
Yeah.
Yeah. Negative 2/3 minus 1 is -3/3. So negative 2 minus 3/3 is -5/3. A little fraction work there. Okay. It's funny, every year I teach this, the biggest stumbling, probably not ripping on you because they're all doing the same thing. The hardest part of this is subtracting fractions. You guys can derive the crap out of calculus stuff, but it's subtracting fractions that freaks everybody out. Okay, notice each one of these functions is one term and one term only. What if we have a derivative of a function that has multiple terms? How do we handle that? Right, you cry. You go right to crying. You don't even attempt it. You just... Oh, we did that already. Let's skip that. Sum and difference rule. So if we take a bunch of terms and we add them up, this is what I said before, that we've talked about this when we did limits and yeah, all these other things. The derivative of a sum is the sum of the derivatives. So you just take the derivative of each individual term, and when you're done, add them all up. Okay. The derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. Easy peasy. So if you want to take the derivative of x squared plus 3x, you take the derivative of x squared, you take the derivative of 3x, add the two together, you're done. However, there is a catch. When we did limits, we had a list of a whole bunch of them. The limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. The product of a limit is the limit of the product, and quotients don't work. Only sum and difference, just plus and minus. Product and quotients opens up a whole different can of worms that you ain't ready for yet. Okey-doke. We good? Moving on. What's the derivative of x cubed minus 4x plus 5? Say.
So it's accurate.
Hmm?
Text is.
Don't overthink it. Okay, you ready?
Yeah.
So the derivative of a sum or a difference is the sum or difference of the derivatives.
Oh, so it'd be x cubed minus 4x plus 5.
Correct? Now take the derivative. What's a derivative of that, x cubed?
1.
So use the power rule.
Oh, 3x
3x
squared.
squared. Right, because 3 minus 1 is 2. Good. What's the derivative of negative 4x? By the way, I realize I'm not really covering things up. Just go with it.
Negative 4x.
No. Michael, help him out.
Negative 4.
Negative 4. X to the first minus 1x to the 0. Ready?
Yeah.
What's the derivative of that? 5.
5. It was 0.
0.
Yeah.
Good. So therefore the derivative is, say that all over again. You forgot it already, didn't you? I don't know if I have it up here. If I.
Alright, so 3x minus 4. Wait.
That next one.
Hey, look what next one. Sorry, didn't mean to scare anybody. I thought I had it typed in here. Okay, so f prime of x is, you said the derivative of x cubed was?
3x squared
Good.
minus 4 plus 0.
Yeah. We're all big people. We don't need the plus 0, right?
Yeah.
All right, good. Everybody okay with that?
Sure.
Okay, good. Sure. You're just saying that to make me feel better. Thanks. Who just threw up in their mouth a little bit? Be honest. Oh, God. G prime of x. Okay. So, if you're having trouble with this, it's actually negative x to the 4th over 2 plus 3x cubed minus 2x. Kate, your turn.
Okay, so it would be negative.
It's a good start.
Negative 2x to the 3rd.
Oh, nice. 1 down, 2 to go.
And then plus 9x squared
Uh-huh. Bring it home.
minus 2.
Outstanding. Let's give it up. That was well done. Everybody follow that? Okay. When you have something like this, don't freak out. Just rewrite it as negative 1/2 x to the 4th. It's the same thing. Okay? Tricky. This should be a 2. I got a little hyper there. Okay, Get this out of the way. I think I might have another example. I don't know how bad it's gonna get. Please don't anybody cry. Oh, wait a second. I must add another one in. Oh.
That's okay.
That's okay. All right. We're fine. Okay. All right. Sine and cosine functions. So remember when I said I don't really like you to just memorize things because, you know, blah, blah. Well, here's another example of you just got to memorize them. There they go. Derivative of sine is cosine. Derivative of cosine is negative sine. That's going to cause some problems. The problem is going to be you're going to have trouble remembering where the minus sign is. And I don't have any clever ways for you to remember it.
Wait, the derivative of cosine is negative sine, but the derivative of sine is positive cosine?
You got it. It is weird. I just work here, man. Sorry. Because that's only 2 of the 6. Right. We got 4 more coming later. But for now, that'll get us started. And once you burn that into your brain, it doesn't require any calculations. You just do it. You see the derivative of sine? It's cosine. You see the derivative of cosine? It's negative sine. Of course, we can complicate it a little bit by... All right, we won't complicate it. I lied. Okay, so don't overthink this. I'm taking 2 times a function, and I want to take the derivative of that. So how do you handle a constant out in front? So Oliver, what's a derivative of 2 sine of x? Not that.
No.
Go away.
2 cosine x.
2 cosine x, that's it.
There we go. That hard.
Uh-huh. No, it wasn't that hard at all. Should we do another one? Some of you are like developing a twitch every time I reach for that. That was coming. Alex, what do you got?
1/2 cosine x.
Okay, that's right. It's reasonable. It's doable. Constant rule again.
That smile is weird.
Wouldn't steer you wrong, right? It's doable. Huh?
You'd steer us wrong.
I probably would, yeah. Ben, what do you got for me?
Well, the derivative of x is 1.
Well done.
Then it's plus,
Good, because the derivative of a sum is the sum of the derivatives.
plus negative sine of x. Yeah, so you really can just
I would
make
keep
that
it real here, yeah. Minus sine. Right? Easy peasy. I was just messing with it. Okay, remember I said there's 3 things for a derivative. The first one we already talked about. It is the slope of the tangent line to the function. Second thing, it's a rate of change. Rate of change of what? Well, it depends on the problem. This is where we'll get some all kinds of fun stuff in here. Blah, 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 da, 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 respect to each other. Applications involve things like, you know, you could do water flow rates, you could do production. We're going to do a lot of problems involving those. In fact, I've got a nice little project that will involve a field trip down to the pool, because we're going to calculate how long it took to fill the pool. Okay, that'll be fun. What's that? You want to go in the pool? Is that what? You go in the
No,
pool?
one instance.
Everybody
It's
hates
too
it.
cold.
Is it cold?
Oh, yeah.
Yeah.
One time I went to
Keep moving.
I'm sorry?
It's like 90 degrees last time I was in
I
there.
think they have a concept for everything. But the
Wanna-
water.
Question?
When is the
No,
slope?
it's a best practice.
When is the slope field trip?
Not for a while.
Oh.
Yeah, when we get to related rates and things like that. So this kind of stuff will allow us to calculate all kinds of fun. How much time it takes to fill the pool. You know, you fall off a ladder, how long will it take to hit the ground. For some reason, a lot of our word problems involve like death and destruction. You know, it's, you know, we'll talk about that later. So, okay. Now we get some physics involved. So that S of t function shows up now. S of t is the location of an object at a certain period in time. So S is the position, I don't know why S is used, and t is time. And we can go through all this blah, 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 but we end up with just, it comes back to the basic dirt equation. You know the dirt equation, right? Distance equals rate times time, but we want it as rate is distance divided by time. Change in time over change in x. That's a rate. Now, what happens when you take the rate of change of the position? What do you end up with? From physics.
Velocity.
Correct, velocity, which we're getting to there. Now, two things we're going to be concerned about. Average velocity and instantaneous velocity. And both can be easily explained talking about a trip to grandma's house. Okay. So you leave your house and you drive 20 miles to grandma's house. Your average velocity is the average distance you drove going to grandma's house. Let's say it's 40 miles an hour. Now, does that mean that every moment from the time you left your driveway to the time you came barreling into grandma's driveway, you're doing 40 miles an hour? Yes or no? No, it's an average velocity. Sometimes you were doing 60, sometimes you were doing 0. But that's an average velocity, okay, which is just this plain old rate equation. However, also, by the way, you can think of it as the slope of the secant line from stuff we've already done. If we want an instantaneous velocity, though, an instantaneous velocity happens at a moment in time. So you're driving from grandma's house and you want to know at 12:03 how fast were you doing? What were you doing? Were you going? Okay, so you look down at the speedometer and we're doing 85 miles an hour. Okay. We really want to get to grandma's house. Okay. One is a derivative, one is just a slope calculation. So that whole idea of secant and tangent line pops up in the physics too, in the form of an average velocity versus an instantaneous velocity. Okay. So now we start dropping things. Blue ball is dropped from a height of 100 feet. Height is given at this equation. That equation should look a little familiar for those of you that had physics. Negative 16t squared plus 100. Acceleration due to gravity, right? We'll get to that later. Find the average velocity over the time intervals. Okay. So I drop a ball. After a second, I'd like to know between 1 and 2 seconds what was the average velocity. It's just a slope. Find f of 1, find f of 2, calculate the slope. Go ahead. Get your calculators out too if you want. So first things first, calculate where that ball is at 1 second. Calculate where the ball is at 2 seconds. And then calculate the slope. Change in distance over change in time. We're not going to do all three of these. We'll just talk about the first one, and I think you'll get the idea. Okay, so you drop the ball. You're 100 feet up in the air, you drop the ball. After a second, how far is the ball off the ground? Dante? 84 feet. Good. At 2 seconds, how high is the ball off the ground? 36 feet. Good. Okay. Starts at 80, what'd you say? 84?
Yeah.
Ends at 36. Calculate the average velocity. 84 minus 36. Okay. And then divide it by 1. Or negative 1, sorry. And you should get a negative velocity, right? Why is the velocity negative? Yeah, the ball's dropping downward. Okay, so I don't really want to do B and C because it's the same thing, it's just repetitive. But does everyone understand what's going on? Okay, good. Now, that's different than asking the question, how fast is the ball going at, let's say, 3 seconds? Okay, that would be an instantaneous velocity. This is the average velocity between 1 and 2 seconds. Okay, we'll get to those others in a second. So, like we did, plug in 1, plug in 2, calculate a slope, negative 48 feet per second. Okay, nothing fancy. And as I mentioned, it's the slope of the secant line. Right, average velocity is the slope of the secant line. Instantaneous velocity would be the slope of the tangent line. Okay, we don't need to see the other ones. Yeah, it's just different numbers, same thing. Okay, beautiful. Now, if we want the instantaneous velocity, we have to take a derivative, which this would not be fun, but we're done with this. We can just move on to that. Okay. So what is the instantaneous velocity? Or I should say, what is the velocity? I'm going back to the function here. What's the velocity of that function? So let's get some notation under control here. I want to know if this is s of t. Try that again. If this is s of t, then what is s prime of t? Say again? Perfect. Which is the same thing for us as the velocity. And you'll recall from physics that velocity can be positive or negative, Greg.
Can we keep the plus 100 in there, or?
No, because what's the derivative of a constant? 0 goes away. So now if I want to know how fast that thing is going at 3 seconds, I just plug in 3 in for t and I get my calculation of negative 96 feet per second. Okay, does that make sense? All right. And then talking a little bit about physics, then we have to talk about the difference between velocity and speed. What is the difference between velocity and speed? Jeremy?
Velocity is direction.
Correct. So if you're asked for speed, it's in this slide here somewhere. Yeah, blah, 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 blah. Oh, there it is. Speed can never be negative. So speed is the absolute value of the velocity. Velocity can be negative or positive. Speed must always be negative. Excuse me. There's a little more to finish in the slideshow, but we can pick up where we left off tomorrow. That's enough to allow you to get most of the homework. Most of the homework tonight is just repetition of practicing this